Hello and welcome to Textbook Engineering Problem. Today we're looking at Elementary Principles of Chemical Processes 3rd edition. We're doing problem number 3.7. I'll read the problem statement. A rectangular block of solid carbon, graphite, floats at the interface of two immiscible liquids. The bottom liquid is a relatively heavy lubricating oil, and the top liquid is water. Of the total block volume, 54.2% is immersed in the oil, and the balance is in the water. In a separate experiment, an empty flask is weighed. 35.3 centimeters cubed of the lubricating oil is poured into the flask, and the flask is reweighed. If the scale reading was 124.8 grams in the first weighing, what would it be in the second weighing? Suggestion: recall Archimedes' principle and do a force balance on the block. Okay, so basically we're looking at differences in densities here. If you have something floating, the oil will have a certain density, the water will have a certain density, and the block density is what decides where the block sits at the interface between the two fluids. Okay, so let's go ahead and do a force balance. Actually, let's start off with a picture. So we've got a certain, let's change this to water. So we've got our water here, and then we've got our oil here, and then we've got a block of graphite. Sitting in the oil. Okay. And then this is the bottom of the container. Okay, so we know the density of water. So the density of the water is equal to 1.000 grams per centimeter cubed. Okay. We know that solid carbon is going to have a certain density, and we can look up what that is in the appendix. So if we look solid carbon up in the appendix, we know that the density of the carbon is equal to 2.26 grams per centimeter cubed. Okay? But we don't know what the lubricating heavy oil is. So we don't know the density of the oil. We do know that this block has a certain volume, and that the volume times 54.2% is submerged in the oil. So that's what we're looking at here. So now let's do our force balance. So we've got our block here, and we've got the buoyancy force. So this is the force, and this is a buoyancy force of the water on the block. And then there's a buoyancy force of the oil on the block for the part that's in the oil and the part that's in the water. And then there's just the plain weight of the block. So we'll call that Fg for gravity. So there's a certain, the block has a certain mass, and gravity is pulling down on that. And the block is not moving. So we know that the sum of the forces on the block has to equal 0. Okay, so from this force balance, we say that the force of the water plus the force of the oil minus the force of gravity equals 0. Newton's second law states that the force equals the mass times the acceleration. In this case, the only accelerating force that we have is gravity. So the force of the buoyancy of water is equal to the mass of the displaced water times the acceleration due to gravity. And the buoyancy force of the oil is equal to the mass of the displaced oil times the force of gravity. And we'll go ahead and move the weight of the block onto the other side. We know that the mass of the carbon times the force of gravity, that's the total mass of the block, times the force of gravity is the weight of the block. Okay? So if we divide by the acceleration due to gravity, that all cancels out, and we're left with the mass of the water displaced plus the mass of the oil displaced equals the mass of the carbon. We also know that the mass equals the density times the volume. So now we convert these into densities and volume. So density of water times the volume of the displaced water plus the mass plus the density of the oil plus the volume of displaced oil equals the density of the carbon plus the volume of the carbon block. Okay, now we can use our information that we gained about our volume factor here and calculate and change things into a total carbon block volume. Okay, so we know that the total volume of oil that was displaced is equal to, I'm going to call 54.2. That's the fraction of the block that's submerged. I'm going to call that alpha O. So 54.2. Or rather, I'll turn this into a fraction. So 0.542. Okay, and then I'll do the opposite for water, because the balance should be water, and that is 45.8. 0.458. Okay, we know that the volume of the oil displaced equals the volume of the carbon times the volume fraction of oil, because that was given to us in the problem. And we know that the volume of water displaced is equal to the volume of the carbon times the volume fraction of the water. Okay, so let's substitute these fractions, or these values, in for the volumes displaced. So we can put it in terms of things that we know and potentially cancel out the volume of the block, because they didn't give us the volume of the block, which means that it's probably not necessary to know what the volume of the block is in the problem. Okay, so the density of the water times the density of the volume of the carbon times the volume fraction of the water, and the same for the oil. Okay, and we can see that the volume of the carbon actually does cancel out here, and we're just left with these volume fractions times the density. Okay, and each one of these terms is known except for one. So we know the value of the density of water, we know the volume fraction, we know the volume fraction in the oil, and we know the density of the carbon. The only one that we don't know is the density of the oil. So let's go ahead and solve for what the density of the oil is. The density of the oil equals the density of the carbon minus the density of the water times the water fraction divided by the oil fraction. And this equals 3.32 grams per milliliter. So that is the density of the oil. Okay, so now the next part in this experiment, we're calculating, kind of doing the density calculation backwards. We have an empty flask, we add a certain amount of volume of lubricating oil, and then we have to figure out what it would weigh in the second weighing. Okay, so normally you would do this the other way around in order to calculate what the density of the oil is. You would get a known volume of the oil, and then you would weigh it, and then you would know the mass over the volume, and then you would know what the density is. So in this case, we're doing this a little bit backwards. Okay, so we know that the volume of the oil in this case is 35.3 centimeters cubed. We know that the mass of the oil in that case would be the density of the oil times the volume of the oil. We just calculated what the density of the oil was. So let's do the density of the oil times the volume, and that is 117.4 grams. Okay, and then we know the mass of the container is equal to 124.8 grams. Therefore, the mass of the container plus the mass of the oil should equal the total mass of what it weighs on the second weighing. Okay, so M2 equals 242.2 grams. Okay. Let's adjust that to significant figures, 242 grams. Okay, so that is the answer to problem 3.7. Thanks for joining me on this problem. If you have any questions or concerns, please put them in the comments below and I'll be happy to respond to you. Thanks for joining me on this problem, and I hope to see you in the next video. Thanks. Bye.